Hi everyone, welcome to Chem 1150. This is Gen Chem for Engineers, and I also saw that the majority of you guys this semester are freshmen, so also welcome to Cal Poly Pomona. This is our very first lecture video for week 1. We're going to be covering significant figures and calculations, unit conversion, and we're going to introduce the periodic table. I'm also posting a PDF of the notes, so I suggest that you print those out and fill them out as I go through this. And also, if you haven't printed out a periodic table yet, or if you have a textbook that has the periodic table, you may want that handy. We're going to be referencing it several times towards the end of today's lecture. Okay, so let's just jump right in. So let's first talk about significant figures. Significant figures are mostly important because they convey information about measurements that we make, and they actually convey nonverbal information about measurements we make. You may not know who's going to read data that you take later, but whoever reads it can know how precise that data is based on significant figures. Some instruments are capable of measuring with greater precision than others. For example, 2.500 grams versus 2.50 grams. Or 7.20 milliliters versus 7.2 milliliters. When making a measurement, it's important to represent that measurement to the correct degree of uncertainty. Measurement should be recorded to the first uncertain digit. For example, 1 place beyond the last certain digit. So in plain English, an easier way to say that is the last number we write is the first number we have to estimate. The digits that are known with certainty plus an additional digit that contains some uncertainty, the one we estimate, are referred to as significant figures, or for short, we'll call them sig figs a lot in the measurement. So let's see some examples of that. So for each graduated cylinder below, how should the indicated volume be recorded? How many digits are known with certainty, and how many sig figs are there in the measurement? Which graduated cylinder is more precise? So let's look at this one on the left first, this one here. So this meniscus, this is what we call this here, this line here, I'm going to kind of draw it in. Actually, I'm going to draw it a little bit above that, something like that. Okay. So we're going to look at that meniscus. So for sure, we can say it's somewhere between 20 and 30, right? Let's give this thing some units. Let's say that this graduated cylinder is in milliliters. For sure, we can say that the volume is between 20 and 30. So without a doubt, we know that the first number is a 2. The next number, even though that meniscus does look like it's on the line, it's actually just above the line. So we can also say with certainty that the next number should be a 4. The last number, though, we have to estimate. So looking at this, if this is just above the line, I would have to estimate its position between 24.0 and 25.0. 25 would be this next line here. So I would estimate that to be maybe 24.1 milliliters. So this one right here is the first number that I had to estimate. So because of that, it's the last number I write, but it's also significant. So for sure, I knew that the 2 was certain, and the 4 is certain, and the 1 is uncertain. And those 3 together give me 3 sig figs. Okay. Now the example on the right is actually the same picture, but just without the zeros on it. So now we're between 2 and 3. So for sure we can say we're somewhere at 2. But because it's between 2 and 3 and not 20 and 30, the decimal comes into play, and our 4 is now 0.4. And then I'm going to keep my initial estimation of the 1. And so now this volume is actually 2.41 mils instead of the 24.1 mils. Again, my 1 is estimated and the 2 and 4 are certain. So I have 3 sig figs total. But then which graduated cylinder is more precise? So the one that's more precise is the one that gives you more detailed information, more information about an easy way to say this is more small information. So more decimal places. So this one gives me information into the hundredths position, whereas this one only gives me information to the tenths position. The first graduated cylinder only gives me tenths. The second graduated cylinder gives me hundredths of a mil. So the second graduated cylinder is more precise. So we can get some practice in counting sig figs. The one thing that usually gives students a hard time with significant figures are zeros. There's three kinds of zeros. There are captured zeros, which are zeros in between two non-zero numbers. There are leading zeros, and then there are trailing zeros. So we'll look at an example of each of those first. So with our first example here, I'll label that number 1, 5.005. These are examples of captured zeros. They are in between two non-zero numbers, and they are always significant. We always count them. So this would have a total of 4 sig figs. Both 5s are significant, and then both zeros are significant. For number 2, these zeros are leading zeros. They are not in between two non-zero numbers, and they are to the left of the first non-zero number. So leading zeros are never significant. They're really just there to tell you about the magnitude of the number, the size of the number. They're basically just saying in this case that 5 is a very, very, very small 5. So here we only have 1 sig fig. Now, in number 3, we have trailing zeros. Trailing zeros can be confusing. The rule of trailing zeros is that if they are after a decimal and after a non-zero number, then they are significant for sure. So these first 2 zeros are actually leading zeros. There is no non-zero number to the left of them, so they do not count for significance. So I'm going to take that away. But the 3 zeros after the 5 occur after a decimal and after a non-zero number, so they do count. So we have 4 sig figs here. Just so you can see, I'm going to erase my lines underneath, okay? So the only 4 that count are these 4 here. The 5 and then the 3 trailing zeros. For number 4, 500. This is probably one of the most frustrating ways to write data because it's the most ambiguous. This can actually be 3, 2, or 1 significant figure. Just by looking at that number, if it was written just like that, we really don't know how precise that number was. So the way that we get around that, the best way to convey how precise that number is to use scientific notation. Scientific notation leaves the magnitude of the number. It's still 500, but we're going to introduce a decimal so that we can say for sure the zeros after the decimal are significant. So in example number 5 here, 5.00, there's 2 zeros after a decimal point. It still is a total of 500 because it's times 10 to the 2, but now I'm explicitly saying there are 3 sig figs. In number 6 example, 5.0, now I'm saying that only the first 0 is significant and not the second. So this would be an example of 2 sig figs. To obtain the correct number of sig figs, it's often necessary to round off a value from the many extra digits on a calculator screen, for example, and we'll come across lots of examples of that. Some of the rules are as follows. Now, these are rules that you have likely used since middle school and certainly in high school, so these should sound pretty familiar. So if the digit following the last sig fig is 1 through 4, we round down. When we say round down, we leave the last significant figure as it is. We don't lower it, we just leave it as the number that it is. If the digit following the last sig fig is 6 through 9, then we round up. Then we bump that last sig fig up by 1. This may be a new rule for you. This is not a very common rule. I'm not incredibly strict on this rule, but I do want to cover it just so that if you see it later, you're familiar with it and you know why we have it. If the digit following the last significant figure is a 5, and there is no other non-zero digit after the 5, we need to round up half the time and round down half the time. The reason for that is that you're right at the 50% mark for that number, and it would be an artificial bias to always round up. Probably what you've always done in the past is just rounded up with a 5. That's kind of the go-to rule in middle school and high school. But technically that's introducing a bias. So if you are truly at the 50% mark, which would be a 5 with nothing else after it, then we need to spend the time, half the time up and half the time down, so that we don't introduce a bias. So the rule that we're going to use is round down if the last sig fig is even, and round up if the last sig fig is odd. So let's see some examples of that. Oh, here's some marks from earlier when I was doing these notes. Get rid of those. Hard time getting rid of them. Anyway, so for the first one, so this whole table we're going to round to 3 sig figs. So for the first one, the 4, the 8, and the 9 are significant. Those are the first 3 significant figures in the number. And then the 6 is the first non-significant number. So that's where we want to truncate it. But because it's a 6, we need to round up. So when we do that, we're going to get 0.0490. 89 will round up to 90. The next one, the 1, the 2, and the 3 are significant. The 4 is not high enough to need to round 3 up. So this is just 1.23. On the next one, 1.235. So here we end in a 5 and there's no other digits after it. So because the last sig fig, which is 3, is odd, and we said that we're going to round up if the last sig fig is odd, we're going to make this number 1.24. 97,510. The 9, the 7, and the 5 are significant. So we're going to round there, and the next digit's a 1, so we don't need to round up. So this is going to be 9.75 times 10 to the 4th power. For 1.225, this is another example where the last digit is a 5. And in this case, we're going to round down because the 2 here, which is the last significant digit, is even. So we'll just leave this at 1.22. For 1.2250, that's the exact same as 1.225. As long as there can be as many zeros here after the 5 as we want, but as long as they're all 0 and none of them are non-zero, that doesn't change the number. So this is still going to be 1.22. For 1.2251, now we have a non-zero digit following the 5. So now you can imagine we're actually above that 50% mark. So now we will always round up. If there is any number other than 0 after the 5, we will round up. And it doesn't matter how far after the 5 it is. There could be 10 zeros there and then a 1. And even that's enough to cause us to need to round up. So both those last 2 examples should be rounded up to 1.23. When doing calculations, significant figures are very important because they'll actually sometimes dictate whether or not you're going to get the right answer. So there are 2 different rules that have to be applied for determining the proper number of sig figs in the result of the calculation, depending on the kind of calculation that you're going to do. So the 2 rules are going to be multiplication and division, and then a different rule for addition and subtraction. The multiplication division rule is the more common one. It's probably the one that you're familiar with already. There can only be as many sig figs in the answer as the factor with the least number of sig figs. So what this looks like, so for example, let's say we're going to do this calculation here. So report with correct sig figs assuming measured values. So we have 8.259 times 1.2 divided by 3.33. And this big long number here is the number that the calculator spits out, but we need to know where are we going to round that. So how many sig figs can the answer have? So our first factor here has a total of 4 sig figs. The second factor has a total of 2. And our third factor has a total of 3. So this factor here that only has 2 sig figs is going to dictate the fact that the answer can only have 2 sig figs. So the 2 and the 9 are significant, and we have to round it. And then because the next digit is a 7, that means our answer is 3.0. For addition and subtraction, this one is more difficult. Only as many digits to the right of the decimal point in the answer as the factor with the least digits to the right. So whatever factor is the least precise is going to dictate the precision of your total of your final answer. So for example, 17.2935 plus 5.66 plus 1.9 is equal to 24.8535. So this has 4 decimal places. Our second factor has 2, and our last factor only has 1. This is the least precise number, so that's going to dictate that we can only have 1 decimal place in our answer. So all the numbers leading up to that position, they're significant. We don't count them out. So it's 24 and then 0.8. So the 8 is significant. And then because it's 535 after that, we're going to round up. So 24.9. If a calculation has both addition and subtraction and multiplication and division, apply each rule in turn in the order that the calculation is carried out without rounding off any value until the final result. This last part is very important. If you round off early, it's very common to come out with the wrong answer at the end. So do not round early, but keep track of how many sig figs each answer should have. So for example, we need to do the addition portion of this next calculation first before we do the multiplication. And when we do that, 6.024 plus 0.43 is 6.454. But because the 0.43 is the least precise number, that means that my significant figures end with the hundredths position. So I only have 3 sig figs there. I'm not going to round it yet, but I'm going to remember that this number technically only has 3 sig figs. So I'll multiply 5.608 by 6.5454, and when I do that, I'll get 36.194. So this second factor in the multiplication has 4 sig figs, but this first one only had 3. So that one will dictate that my answer can only have 3 sig figs, so that will be 36.2. That's our answer. The next sheet, in 2 pages, there'll be some practice on this, and I'll be posting a key, so you'll be able to get plenty of practice between the key, the homework, and then of course the quiz, which will come live, I believe on Friday. I'll have to check the schedule. Okay, so for, excuse me, dimensional analysis. Dimensional analysis is a very fancy way of saying unit conversion. One way to approach many of the required calculations that we're going to need to do is to use dimensional analysis. In dimensional analysis, the units of a known quantity are converted to the units of a desired quantity through a series of conversion factors. So we start with the quantity that has been given in the problem, and we systematically convert from the starting units to the units that the problem is asking for. Units cancel out when they're on opposite sides of the division line, above and below. So we'll use T-charts. I'm a big fan of T-charts, and I'll T-chart most of our workout. Here's just an example from your textbook of the kind of units that we'll be using, and some of the prefixes that you'll also want to be familiar with. So mass is a kilogram, time is a second, distance is a meter, electric current is an ampere, temperature is a Kelvin, number of particles a mole, we use that one a lot. And then probably the most common prefixes that we use are for a milli, probably won't get into femto very much, but definitely down to pico, and then kilo and mega. The rest are good to know, but none of this is stuff that you really should be very new at this point. Okay, so let's put this into practice. So, for example, how many seconds are there in 7.5 years? So there's 2 things we need to focus on here. First of all, what are we told? So what do we know? So we know we're going to start with 7.5 years. And the other thing we need to know is, what are they asking for? What are we trying to get to? So we're trying to get to seconds. Our goal is to convert down to seconds. So there are going to be some conversion factors in the middle there. So this is what I like to call a T-chart. So I start with 7.5 years. So my next, oops, oh gosh. Okay, so my next example, my next conversion will be years towards seconds. So what might be the next conversion that I can use? Off the top of my head, I don't know how many seconds are in a year. That's probably not information that we usually carry around, but I do know that there are 365 days in 1 year. And then I know that there are 24 hours in 1 day. I know that there are 60 minutes in 1 hour, and you can see how I'm just breaking this down to the next easiest conversion factor that I know. Then from minutes, I know that there are 60 seconds in 1 minute. And that's actually as far as I need to go. So now I have seconds on the board, and that's my goal, so that's good. And I can go through and I can cancel out. A common mistake made with these T-charts is writing these factors upside down. So the way that you know you wrote them the right way is if everything cancels. So always, before you carry through the calculation, always go back and check and make sure that your units cancel. So my years here cancel, my days here cancel, hours cancel, and minutes cancel. So I'm left with an answer in seconds. And as far as significant figures go, our answer should only have 2. That's because all of these are what we call exact values. And we'll explain exact values a little bit more here at the bottom of the page, but the 2 for the significant figures is going to come from the 7.5 years. So when I do that, I get 2.4 times 10 to the 8 seconds. Excuse me. The mass density of water at 25 degrees Celsius, which is about room temperature, is 0.997 grams per milliliter. A child's swimming pool holds 346 liters of water at this temperature. What mass of water is in the pool? Okay, so now there's more information in this example than there was in the last one. But still, I know that I'm starting with 346 liters, and I want to get from liters to some unit of mass. So that could be grams or kilograms. So let me set up a T-chart. Now, the other piece of information that I'm given is the density of water, which is in grams. That's mass, so that's good, per milliliter. Now, I can already see that the pool volume is given in liters, and this conversion for density is in milliliters. So the first thing that I'm going to go ahead and do is use the conversion from liters to milliliters. Okay, that'll cancel out my liters, and now I'm left with mils. And then I'm going to use the density value that I'm given. So I want my mils to be on the bottom, so I'm going to write it as it's given, 0.997 grams per milliliter. Cancel out my milliliters, and that leaves me with a unit of mass on top. So this is equal to 3.45, 3 significant figures, and the 3 sig figs are coming from this value here and this value here. That value is actually rounded off, so 3.45 times 10 to the 5th grams, and if you wanted to convert that to kilograms, you could, and you would get 345 kilograms. So a little bit more about those exact values. So for example, this one here is an exact value. Some values that are used in calculation are not measured, rather they represent an exact relationship that contains no uncertainty. For example, 7 days in a week, 2 atoms of hydrogen in a water molecule, 1,000 grams in a kilogram. It is useful to think of such exact values as having an infinite number of sig figs, since they do not impose any limit on the number of sig figs in the final calculated value. So which of the above values in the above calculations were exact values? So our 1,000 mils to a liter was exact, and then Our days to year, hours to day, minutes to hour, and seconds to minutes were all exact. And interestingly enough, even if you wanted to talk about the fact that a year has a little bit over 365 days, thus the leap year, you would still come out to the same answer here with the same precision because of sig fig. So you can try that. If you're familiar with that, go ahead and run that through and see what you get. You should get the same answer. Intermediate values and calculations. At times it may be convenient to calculate an intermediate value as part of a longer calculation. In such a case, you should keep at least 2 extra digits beyond those required by the sig figs in your intermediate value, and only round the proper number of sig figs for the final reported value. Failure to do this may result in a rounding error. This is very common, and it's a little bit difficult to get used to, but with practice, you'll get better at it. I like to, let's say that I have a long number like 1.4523, and let's say that I know that it's only significant to the 5. I like to overline the last sig fig there, just to remind myself that, hey, that's the last significant figure. I'm going to use the whole number in my calculation, but that just glancing at that tells me that this only has 3 sig figs in it. If that makes sense. Okay, so here's that self-study page that I was talking about. I'll be posting a key to this. Hopefully by the end of Thursday, maybe by the end of Friday. So go ahead and give these a shot in addition to your homework. And that's just a little bit extra practice on that for you. So that's going to wrap up the math review that we're going to do. I know that the math review that you have on your homework is a little bit more in depth. So use that to your advantage. There are multiple missed attempts allowed on the homework. So I know that the homework is harder than what I'm actually going to cover in lecture. And that's because that's where the bulk of your individual learning is going to happen. So ask questions if you have them, but understand that you are allowed, I think it's 6. You can get the answer incorrect up to 6 times before they finally pull the plug on that particular question for you. So don't exhaust all 6 attempts. Ask some time before your 6th answer. Okay. So now we can introduce the periodic table. So the periodic table is iconic, right? That's what we think of when we think of chemistry. The periodic table is a very useful way to organize all of the known elements in the universe. The elements are arranged in order of atomic number, and we'll be defining that, and lined up so that elements with similar chemical and physical properties are in the same column. It then becomes apparent that these properties of the elements repeat themselves in a very regular fashion. That is to say, a periodic repetition of the element properties in each row of the table. On most periodic tables, the atomic number is indicated above the element symbol, and the atomic mass is indicated below the symbol. So what that might look like, if you pull any square, for example, I'm looking at this square here. If you pull any square, any element from the periodic table, the large letter that's in the middle, or combination of letters, for in this case this is just a C for carbon, but for example Si is silicon, the atomic number is above that letter, and then below is a number that is always bigger. So if you're not sure which is which, the number that's bigger is always the atomic mass, and the smaller number is always the atomic number. The 2 most common systems used for labeling the columns are shown at the top of the periodic table. So most commonly you'll see, especially in like chemistry and physics textbooks, you'll see this 1A, 2A, 3B, 4B, 5B, that classification system there. And then I've noticed that in a lot of engineering textbooks that they just use the 1 through 18. The 1, 2, 3, 4, 5, and on through 18. So both of those classification systems are in use. Neither one is more correct than the other, but just understand that if you see one or the other, they're referring to the same thing. Okay, so let's label the following on the periodic table. A group is a column. So a group is the same thing as a column. So for example, and I'm going to highlight and then erase because this may get a little messy. So for example, this would be a group. This would be group 1A, or this could be a group here. This would be group 4A. So a group is the same thing as a column, and a period is the same thing as a row. So there are a total of 18 different groups, and there are a total of 7 different periods. So a period would be, for example, here. And then a period is even where it's truncated. So where there's a bunch of elements missing in the middle, that's still period 2, for example, and this down here would be period 4. So a period is the same thing as a row. Metals versus nonmetals. This is what this dark bold line here is used for. I'm going to outline this as carefully as I can. Everything to the left of it is a metal, and everything to the right of it is a nonmetal. So the ratio of metal to nonmetals is about 3 to 1, and these two rows of elements down here, they're taken out from right here. So these are included in the metals. Okay, so this dark line here represents where they're taken out from the bold line. They're taken out from the bold line in the periodic table. Okay, so let me erase those notes. Main group elements. This is where the chemistry system of classification makes this a little bit easier. Main group elements are everything that ends in an A. So 1A, 2A, and then all of these, 3 through 8A. All of these are main group elements, and they're referring to the groups. So that means all of these, and then all of these are main group elements. Transition metals are all the groups that are classified with a B. So maybe just for clarity, I'll switch colors here. So for my transition metals, I'll rewrite that with a green B. And that would be all of these. Inner transition metals, let's see, I'm running out of colors. C. Inner transition metals are these 2 blocks of elements that get pulled out of the periodic table, and they're almost always shown below the periodic table. So those are our inner transition metals, and we're going to break them down more. So we have alkali metals. We'll cover those now. So we have lanthanides and actinides. The lanthanides, L, are the top row of the inner transitions, and the actinides are the lower row. So these are all the actinides, and then these are all the lanthanides. Okay, so now we'll come back up and we'll finish brown. The alkali metals and alkaline earth metals, I'm going to have to erase some of these notes, refer to group 1A and 2A. If I call this one AM and this one AEM, this first column is AM and the second column is AEM. And it's referring to the whole group there in both cases. Our halogens refer to group 7A. Over here, our halogens. And then our noble gases are referring to group 8A. Okay, so you'll want to memorize how this periodic table is organized. But this is as in-depth into classifying the periodic table as we're going to get. You can use this periodic table down here to help you take notes on where everything was if the top one got a little bit too messy or too busy. Okay, so this lecture has been pretty short, so I'm actually also going to cover just a little bit of the atomic makeup, modern atomic theory. I'm just going to introduce each subatomic particle. This will go by quickly, and this will help us make sure that we don't fall behind in this semester. So modern atomic theory. Protons and neutrons are nearly identical in mass. This is just facts that I'm giving you. Protons and neutrons are about 1,836 times more massive than electrons. So the atom is made up of a nucleus, and in the nucleus, this is that very small center part here, this is where protons and neutrons reside, and then the rest of the atom, this fuzzier outer ring, is where the electrons reside. Protons and electrons carry the exact same amount of charge but are opposite in sign. Protons are positively charged and electrons are negatively charged, and neutrons have no charge. So when we refer to the charges on protons and electrons, we usually just say +1 and -1. That's the language that we'll be using. The relatively tiny electrons move about the nucleus and take up most of the atom's volume, while the nucleus contains most all of the atom's mass in a very small volume. The relative size of a nucleus in an atom is roughly the same as that of a pea suspended in the center of a large domed stadium. So if you can imagine that, that's kind of giving you an idea of the size differences between the nucleus and then the atom as a whole. Here are some more information on the mass and the charges of each of these numbers. You do not have to memorize any of this. This is just to kind of give you an idea of how small these things are. So electrons are about 9 times 10 to the negative 28 grams, while protons and neutrons are about 1.7 times 10 to the minus 24 grams. So they are more massive than electrons, but still they are very, very tiny. And then when it comes to charge, we're mostly just going to worry about the +1 and the -1 charge. The actual charge is given there in coulombs, though, if you would like to know. And the neutrons have no charge, so we say that they have a charge of 0. So we can describe each of these subatomic particles in a little more detail. The atomic number, I said that we were going to define that earlier. The atomic number is what's listed on the periodic table. That's often referred to just as Z. You'll see that a lot. So Z is synonymous with atomic number, and it is equal to the number of protons in the nucleus of an atom of a given element. So what that means is that the atomic number defines the identity of the element. No two elements have the same atomic number. The atomic number is written as a subscript to the left of the symbol. So, for example, if you hear somebody say that a certain element has an atomic number of 6, then that will always be carbon. Carbon cannot have any other Z value than 6. If the Z is 7 instead, then we're not talking about carbon anymore, we're talking about nitrogen. So Z is always equal to number of protons, and it dictates the identity of the element. You'll also notice that in the periodic table, the elements are ordered according to their atomic number. It's increasing from 1 up to 118. So let's fill in the table. Element symbol, Z, and number of protons. So I know that Z is always equal to the number of protons. So if I know that the number of protons are 22, then I know that Z is 22. And if I look on the periodic table, I'll see that I'm talking about titanium, Ti. And then we always write the atomic number as a subscript to the left of the symbol. So it would look something like that. If my Z is 92, then I know that that also means my number of protons is 92. And if I look at the periodic table again, that is uranium, U, and then we write 92 to the left. Electrons in a neutral atom, so if we just say the element as its name is given on a periodic table, that usually means that we're talking about a neutral element. So in a neutral atom, the number of protons is equal to the number of electrons. When referring to elements, it is assumed that one means neutral. We change the way we say the element name if it's not neutral. And we'll be getting into that later when we go into ions. Positive and negative charges cancel one another out in an algebraic sense. So an atom with 2 + 1 protons for a total of +2 and 2 electrons for a total of -2 has a net zero charge. So +2 + -2 is equal to 0. So whenever you're doing this kind of math between protons and electrons, it should be very simple and just whole numbers. We're almost never going to be working with any kind of a fraction. And in the case where the net charge is 0, we say it's neutral. So we can fill in this table. So we know that the element we're talking about is oxygen, which has a Z of 8. It's written here anyway. So this is 8, and we can look on the periodic table to confirm that, which means that there are 8 protons. Now, because this is neutral, the number of protons will equal the number of electrons. So I'm just going to make a little asterisk. Only if neutral can you make the assumption that the number of protons is equal to the number of electrons. So the next line, the only hint we're given is that the number of protons are 18. So I know that that means the number, that Z must be 18. And I also know that we're dealing with neutral atoms in this example, so there must be 18 electrons. And if I look at the periodic table, I'll see that that's argon, so Ar, and then I would write 18 to the left. Under some circumstances, atoms can lose or gain one or more electrons to form an ion. An ion is a charged atom in which the number of electrons is not equal to the number of protons. So we're going to not have a net charge of 0. We're going to have a net charge of some whole number. Note that electrons can be gained or lost relatively easily because they're on the outside of the structure of the atom. When we get into things like electromagnetic radiation later, we'll talk more about that. In normal chemical reactions, a proton, though, is never gained or lost. The only examples of protons being gained or lost that we'll get into is if at the end of the semester, if we're not running behind, if we're running on time, then we'll cover a little bit of nuclear chemistry. So we have 2 different kinds of ions. We have anions and cations. An anion, if a neutral atom gains one or more electron, an anion is formed. An anion is a negatively charged ion in which the number of electrons is greater than the number of protons. So my number of electrons is greater than my number of protons. So my atom should be negatively charged. On the flip side, if a neutral atom loses one or more electrons, a cation is formed. A cation is a positively charged ion in which the number of electrons is less than the number of protons. So in this case, our number of electrons is less than our number of protons. So fill in the table. So now you'll see, now our oxygen symbol here has a new number. It's written as a superscript to the right, and that's the charge. So this is where we write the charge. Since it's oxygen, our Z is still 8, and our number of protons is still 8, and we should still have a small 8 as a subscript to the left. But now we have to think about electrons. So in this case, we can't change the number of protons, because if you change the number of protons, then you change the element. So it has to be 8 protons, but we need the total charge to be -2. So we can only do that if we have 10 electrons. So a +8 plus a -10 would give us a total net charge of 2-. In the next example, we're told that we have 79 protons and 76 electrons. So now we have more protons than electrons. So we have more positive things than we have negative things. So this is going to be a cation. If the number of protons is 79, then I know that my Z is 79. And if I look at the periodic table, that tells me that I'm dealing with gold. And I'm going to write my 79 to the left. But now I have to figure out what my charge is. So now I have +79 plus a -76. So when I do that, I get +3. So this can be written as +3 or 3+. I can't remember off the top of my head right now which way Cengage prefers it. Just pay attention to the question. If it has any ions, it'll say either 2+ or it'll either say +2 or 2+. You should never get an answer wrong for doing it that way. It should prompt you to correct that. It'll give you a little bit of feedback. It'll ask you to reformat your charge. But there are 3 intro assignments that are due by Sunday, so make sure that you don't wait till last minute to get to those, that will teach you about formatting and how to do your homework assignments. They're not actual chemistry assignments, but they just talk about how to do them. So make sure you do those so you're familiar with them before you actually start your homework that has chemistry in it. Okay, our last subatomic particle are neutrons. Atoms of a given element must all have the same number of protons, but different atoms of the same element can have different numbers of neutrons. Atoms with the same number of protons but different number of neutrons are called isotopes. So if we have the same number of protons but different number of electrons, those were called ions. And if we have the same number of protons but different number of neutrons, these are called isotopes. So for example here, these three examples are for hydrogen. So protium is 1 proton and no neutrons. Deuterium is 1 proton and 1 neutron. And then tritium is 1 proton and 2 neutrons. So you can see that the mass, something called the mass number, is changing in between each of those. And so we're about to define that. In most cases, the difference in the number of neutrons makes only a slight difference in the chemical reactivity, but it does change the mass. So we have something that we're going to define as the mass number, and the symbol, the alphabetical symbol that we use for that is usually just capital A, and it's equal to the number of protons plus the number of neutrons. And we write that above the atomic number. So up till now, we've been writing the atomic number here as a subscript to the left, but now we're also going to have a superscript to the left, and that's going to be the mass number. So if you look at this, you can say that your mass number minus your atomic number, that is going to be equal to your number of neutrons. The mass number is so named because the protons and neutrons are responsible for nearly the entire mass of an atom. The mass number, however, is not the same as the atomic mass, and we'll be defining that in next week's lecture. It's always an integer. It's always a whole number. There's never a decimal here. So fill in the table. This is the last table that we'll be doing. So now we're going to have our mass number and our atomic number. So our first line is referring to carbon. And sometimes you'll hear us say carbon 14. You might even see this written. I'm just going to make it a little asterisk here. You might see this written as C14. Okay? When you see it written that way, it's referring to the mass number because it's referring to a specific isotope. So since it's carbon, I know that my Z is 6, and I know that my number of protons is 6. Notice that there's no charge indicated in the upper left-hand corner. So given the information that I'm given, I have to assume that it's a neutral element. So I know that my number of electrons must be 6. But now I have to figure out how many neutrons I have. So my mass number, my A, is 14. And remember that the number of neutrons we can get from A minus Z will equal our number of neutrons. So 14 minus 6 is 8, so we have 8 neutrons there. In our next example, Z is 82, so automatically I know that that also means that I have 82 protons. And in this case, I am told the number of electrons is different than the number of protons. So I know that I'm dealing with an ion, and I'm also told my number of neutrons. So A, I can figure out what A is now. A is going to be my number of protons plus my number of neutrons, and this is a shorthand way for writing neutrons, N with a little 0. And so that's going to be equal to 82 plus 124, and that is equal to 206. Oh. Yeah, 206. Sorry. Okay. So now the last thing that I need to figure out is what's my symbol? What element am I actually looking at? So if I go to the periodic table and I look at atomic number of 82, it's lead. So, oh man. So Pb, and I know that it's 206 is my mass number, 82 is my atomic number, and now I have to figure out what my charge is. So my charge is a plus 82 and a negative 80. So this is 2 plus as my charge. Okay, and that wraps up our lecture for our first week. So don't forget to make sure that you read the syllabus in its entirety. Email me if you have any questions. Go on Cengage and make sure you complete the assignments and the quiz, all of which is due by Sunday at midnight, okay? All right, that's it. I'll see you guys later.